Welcome to the Explainer. Look, if you're working with critical network infrastructure, you already know the drill. A single failure can literally cascade into absolute chaos. Today, we're taking technical documentation and transforming it into a crystal clear, actionable breakdown of Ethernet ring protection switching, or ERPS for short. Let's unpack exactly how this protocol keeps your network alive when things go wrong.
Okay, let's look at our roadmap for today. We're going to cover 1. Introduction to ERPS. 2. Nodes and port states. 3. Control versus data VLANs. 4. ERPS protocol messages. And finally, 5. Timers for network stability.
All right, Section 1, Introduction to ERPS. So how do you prevent a broadcast storm from crashing an entire Ethernet ring? Just consider the absolute nightmare of an unmanaged loop for a second. If traffic doesn't have a designated stopping point in a ring topology, man, a broadcast packet will just circle endlessly. It multiplies, it chokes out all your available bandwidth, and ultimately, it completely crashes your network. We absolutely need a rapid response protocol to survive this.
Enter our hero, ERPS. Now it operates on the international ITU-T G8032 standard, which is great because it plays nicely with all different kinds of vendor equipment. It's exclusively designed for Ethernet rings, and it breaks those devastating loops by purposely blocking a specific port. But the real game changer here? Its crowning achievement is a lightning-fast 50 millisecond recovery time. I mean, that is vastly faster than legacy protocols like Spanning Tree.
Moving right along to Section 2, Nodes and Port States.
In a standard ERPS ring setup, it's pretty easy to spot the traffic cop of our network sitting right up at the top. That's our RPL owner. The other switches you have in the ring, those are just your standard, normal nodes. Let's actually break down exactly what each of them does.
It helps to contrast the active loop-breaking authority of the RPL owner with the passive role of those normal nodes. So your RPL owner is typically going to be your main Layer 3 device. Think something like an MX series router. Its absolute main job is to actively discard a link to break a loop. Meanwhile, your normal nodes, which are usually standard Layer 2 switches, well, they just sit there in the ring passively monitoring the links, looking for any sign of a disconnect.
Now, the ports on these nodes basically exist in one of two protocol states. The forwarding state is exactly what it sounds like. Business as usual. It forwards regular user traffic alongside our ERPS protocol packets. But the discarding state? Think of that like a strictly controlled roadblock. It completely stops all regular user data from passing, but, and this is key, it always lets those emergency ERPS protocol vehicles pass through.
Okay, I really want to emphasize this next point because it causes endless headaches in the field. Discarding is a protocol state, not a dead physical port. Seriously, a discarding port might physically show as up on your dashboard, but on the protocol layer, ERPS has securely locked it down to prevent a loop. Don't let that trick you.
All right, on to Section 3, Control versus data VLANs.
So ERPS absolutely requires a strict separation of duties within the ring. It gets its own dedicated control VLAN, say VLAN 4094, and this lane is exclusively reserved for ERPS protocol messages. User data is strictly forbidden here. Everything else, from your IP RAN to your LTE data, has to travel on separate data VLANs. This setup is brilliant because it ensures ERPS always gets priority communication, with absolutely zero interference from heavy user traffic.
Next up, Section 4, ERPS Protocol Messages.
To really grasp ERPS, we kind of have to decode its alphabet soup. First up is NR plus RB, which stands for No Request plus Route Block. You can think of this as the network's steady, rhythmic heartbeat. Whenever the ring is idle, normal, and healthy, the RPL owner sends this message out. It's basically telling all the nodes, hey, everything's fine and the loop-preventing roadblock is securely in place. Next, we have SF, or signal fail. And when I say this message is urgent, I mean it is absolutely critical. If any node out there detects a physical link disconnect, it instantly blasts out an SF message. It's the alarm bell for the whole ring. The very split second this message hits the network, it tells the RPL owner to unblock its port. And that kicks off the entire 50 millisecond recovery sequence to keep your data flowing. Finally, there's NR, or no request. Once that broken link is physically repaired, the nodes stop sending those frantic signal fails, and they send this NR message instead. But here's the catch. While this acts as the all-clear signal, the network doesn't just instantly snap back to its original state. That deliberate design choice actually brings us right to our final mechanism.
Which is Section 5, Timers for Network Stability.
To prevent chaotic network flapping when a physical link is just bouncing up and down, ERPS uses 3 really strict timers to forcibly inject some patience. First, the hold-off timer. That one delays the initial failure reporting, just in case the link instantly comes right back up. Then, the guard timer blocks outdated ERPS messages immediately after a recovery, so you don't get ghost alarms. And third, the wait to restore timer makes sure the network waits calmly before reapplying that roadblock at the RPL port.
Let's emphasize this specific number for a second, 5 minutes. That is your standard wait to restore duration. The RPL owner will literally wait a full 5 minutes after hearing the all clear before it blocks its port again. It's your ultimate safeguard, preventing a faulty, bouncing link from just endlessly resetting your topology and destroying your network's performance.
So just think about that. No more massive broadcast storms. No more endless, crippling outages just from a single flipped fiber. Just a clean, highly structured loop protection protocol doing its job in 50 milliseconds. By mastering these exact switch mechanics and stability timers, how completely could you transform your own network's resilience? Thanks so much for joining this explainer, and I really hope this equips you to go out and build stronger, far more reliable networks.